Hi, I am Sergio and I'm going to present the work A Semantic Framework for PEGs. This is joint work with Carlos Olarte. PEGs are a recognition-based formalism. We can see a PEG grammar as both the description of a language and the description of a parser for this language. Below we have an example of a PEG that recognizes the non-context-free language that consists of a sequence of A's, B's, and C's. So here we are using PEG predicates. So the start rule has a predicate where it checks if the input matches uh, if rule R1 matches the input. So rule R1 matches if the input has the same amount of A's and B's. So the input has starts with the same amount of A's and B's and is followed by a C. So the predicate succeeds and does not consume any input. So after matching the predicate while still matching the beginning of the input, so we'll match a sequence of A's with this expression highlighted. Then we'll match a sequence of B's and C's, and finally you'll match the end of the input. Here we have the rules related to the order choice. On the left we have a rule where the order choice succeeds because the first alternative of the choice matches a prefix of the input x, so the result is a suffix y of the input. On the right side we have a rule related to that is used when the first alternative of the choice fails. So when it's not possible to match the input by using expression E1, we'll try to match the input using the expression E2, and only in this case we'll use the second alternative of a choice, only if the first alternative of the choice does not succeed. So if the matching of E2 succeeds, S will be a suffix of input X, otherwise it will be a failure. So as you can see, the order of the alternatives it's important here. So the expression AC or ABC matches the input ABC. So the first alternative fails, then the second one succeeds. But the expression A or AB followed by C does not match the input ABC, because A succeeds, the first alternative, then you fail to match C, but will not going back to the choice to match the second alternative, because you have a limited backtracking in PEGs. So these are some advantages of PEGs. So you have no ambiguity, the passes are deterministic, and you can use PEGs to define both lexical and syntactical elements. So you don't need to use a separate lexical or a separate formalism. And what are the disadvantages of PEGs? So on the negative side, you have that it's may not be obvious to see what's the language associated to a PEG. As you have seen before, this input, this string AB, does not belong to the language of this PEG, because the first alternative always succeeds for this input, so the second alternative AB is never tried. So in a general way, if the first alternative of a choice matches prefix of the second alternative, so we will not use the second alternative of a choice. So the second alternative will not match inputs that start with this prefix. So, and here we have another example. The repetition PEGs is greedy, so the language of this expression A star followed by A is empty, because A star will consume all the A's in the input, so there is nothing to match. There is no way to match later. The matching of A star finishes. another negative aspect of PEGs is the backtracking. Although PEGs have a local backtracking, you can have some inputs where the parser needs to backtrack a lot. So we are here, we'll see now an example of a PEG where we highlighted in blue expressions associated with a useful backtracking, and the expressions highlighted by red are associated with a useless backtracking. A backtracking is useful when failing to match this expression indicates that it's still possible to recognize the input in case the parser backtracks. So if you fail to match if, else, or if these expressions, the parser may backtrack and still recognize the input. Otherwise, if you fail to match the red expressions, will not match the input, but the parser will still backtrack and try another alternatives. This is what you call useless backtracking. So making this backtrack will not lead the parser to recognize the input. So to better understand this problem of backtracking, we decided to use rewriting logics. So by using rewriting logic, we can give a uniform and general view of cuts in PEGs. That's it. How you can avoid this useless backtracking PEGs, and you can have a better understanding of a PEG's language. Rewriting logic is a executable specification of PEGs. So you have a formal tool that is executable. So when you are matching a PEGs using a rewriting logic specification, we are indeed building a proof that a given PEG matches a given string, or a proof that that string belongs to the language of a PEG. So here we are reviewing the rules that related to another choice in PEGs, and you can see the rules that we will write for using rewriting logics. You can see that what you have written in a piece of paper, rules odd 1 and odd 2, are very close to the all specification, rules choice 1 and choice 2. Indeed, the rules are the same. There are just a minor syntactical difference between them. So let's come back to the problem involving backtracking. So you need here to distinguish between a regular failure and an error. So the blue expressions indicate a failure, while the red expressions indicate an error. So what's our goal here? It's to signal an error every time you fail to match that red expressions, because the parser should not backtrack anymore. So we'll use these new expressions, an up arrow that we call a true operator, that it will just to an error. So for any input, it's the result of using this expression, it's an error. So when you are evaluating another choice, in case the first alternative of a choice throws an error, the second alternative is not tried. So we are here avoiding a backtrack. We are avoiding to try alternative paths, because we know that these paths will not lead to recognizing the input as valid. So as you explained before, we should associate a true operator with the failure of every read expression. So here we are just associating a true operator with the statement expression of the else branch. So in case the statement after the else does not match, we will throw an error. So we will not try the second alternative of this statement. Actually, we will not try any other alternative of this statement. So the parser will just finish after throwing this error. We will not try any other alternative path. So the usage of the true operator is similar to throwing an exception in a programming language. We can also use this mechanism to model local errors by adding some catch expressions. So in this case, a statement maybe you have three alternatives related to a statement. In the first alternative, you need to match the first alternative, you need to match an identifier followed by a column. So in case you fail to match this column after the identifier, we know the second alternative will not match because the second alternative does not start with matching an identifier. But the third alternative of an statement can match, can begin matching an identifier. So because an expression an identifier may be a valid expression. So we want to, in case you fail to match the column after ID in the first alternative, you want to avoid trying to match the second alternative, but we still want to match the third alternative. So we will put a catch mechanism around the two first alternatives. So after, in case you fail to match the column, you throw an error, so the second alternative will not be tried. The catch mechanism will convert this error into a regular failure, so you try the third alternative of a statement. So to evaluate our approach, we have manually inserted the cuts, the added the two expressions to some peg gammas. So, and we report the number of rules applied by our mode parser for syntactic valid and invalid files. So we considered files in three different languages: JSON, C, and Titan. So on valid inputs, we notice that's a little overhead, and on valid inputs, we could see that the parser saved us a good amount of work. In case of C, this amount varied between 2 and 11%. In case of JSON, it was somewhat higher. So the test cases are available in this repository. So to conclude, we proposed a rewriting logic specification to formally start the behavior of pegs, and used it to model local and global errors in pegs by using by annotation of gamma with the cut expressions, the true operator. Our peg parser could reject invalid inputs faster. As a future work, we intend to apply a technique to automatically insert cuts throws in a peg gamma, so you can preserve the gamma clarity, and all rewriting logic framework can be useful to prove that we are inserted these two operators in the right places. That is, we are not changing the peg gamma, we are not rejecting inputs that you should otherwise accept. And you could also explore the usage of our rewriting logic framework as a derivative parser, and how global cuts can impact the memory used in peg parsers. That is, many thanks.